三星，三星。
对啊，洗饭，我有在睡。
昨天上课，昨天有上课，几点？然后上到几点？
上到3点8点，然后来就是
上到几点呢？
上到5点。
全部人知道今天有补课，不知道，还有个奇怪。Okay, maybe only 3 of us. We just do some exercise first, see if more will come later on. Do some double integral exercise. Double integral. Try to find the volume of the solid that lies above the cone that equals to square root x squared plus y squared, and below the sphere x squared plus y squared plus x squared. Hello. Morning. Okay, if you are not given this diagram here, do you know how to draw this picture? No idea. Okay, so we could start with this sphere first, right? So what's this sphere? X squared plus y squared plus x squared equals to z. Okay, so you need to find the center of the sphere first. So if I throw away the z squared, right, it is like the circle. Okay, so you need to try and factorize it into the square of factors of the coordinate. So what do I mean by that? Yeah, so what do I mean by that? So you can move your z to the other side. Okay, then what? How to factorize the z into a square of something? Of x square, completing the square. So what's the thing? What's the number you need here? 1/4. 1/4. Let me think. So see if we can factorize this. So this will become z minus. Okay. So what does this mean? So this is a sphere centered at 0, 0, half. Okay, with radius 1/2. The center of the sphere should be 0, 0, half. Okay, with radius 1/2. Okay. How about this cone here? Okay. How about this cone? So first of all, you need to know where your x and y lies. Right. Your x and y is the horizontal plane here.啊，这个才只有3个人。Okay. Yeah. All right. So, how do you draw this cone? How do you understand this cone here? What is square root x squared plus y squared? This is the hypotenuse of a right angle triangle. Right? Okay. Okay. How do you see this cone there? So this height is defined by the length of your uh, point, right? Length of your point xy from the origin. Makes sense or not? So let me draw some picture for you. Yeah. Okay, so I need to pick some point from the xy plane. So let's pick 1, 1 here, 1, 1. And then this is the length of this vector here. Okay, so what's the z? So z, we take square root x squared plus y squared. So what's the height of 1, 1 in this case? Square root. So this is our new point. 1. Okay. Yeah. Yeah. So you could imagine what this function do, right? So you imagine you have a whole plane here. Okay, you have a whole plane here, right? And then for each plane, for each point, you attach a height. Okay, you attach a height. What is this height here? This height here is the length of the vector of the point. Okay, so what can you observe first of all? Who has the same length with 1, for example? 0, 2, you sure? For example, uh, minus 1, 1, right? Minus 1, 1. Or minus 1, minus 1. Or 1, minus 1. Okay, what's the similarity here? They are living on the circle, right? Circle of radius square root 2. Okay, so within this, so if you lie on the same circle, okay, you will have the same height of the radius of the circle. Yeah. So starting from the origin, you have 0, and then away a circle, a points on the circle with radius r around the origin, you will have height r. Imagine the shape like this. This, okay, and then like this, and then like this, and then like this. Then you can join these circle together to form the cone. Yes or no? Does it make sense? Question? Yeah, why must straight? Why must straight? Why must straight line? Why is it a straight line? Is it straight line? Why the cone doesn't look like this maybe? Maybe it looks something like this, like a gusting turbo. Why? So if you want to talk about this straight line, right? I think you should talk about the either zx or zy plane. Correct. Zx or zy plane. You want to look at the gradient. You want to look at the gradient. Okay. Maybe let's try. Okay, let's try. What is differentiating x with respect to the two direction, x and y? So that. So what is fx in the x direction? So you got to look at maybe this direction here. What's the gradient? Kernel. Is the gradient like this? Like this? Okay. So what's this gradient? Differentiate this. So partial differentiate x squared plus y squared Let's see what's this. This one. Over x squared plus y squared square root. Is it equals to x over square root? This useful one. This one. Think. Straight. Y equals 0. What do you mean? You mean if you want to fix a plane, is it? Let's fix a plane. Right. So we have like this is in x direction, right? So all of these are in x direction. Okay. So we can fix on zx plane. So for example, on zx plane, what happened? Where y equals 0. Okay, what do we get? This differentiation here becomes what? X over square root x squared, which is, yeah, which is 1. Okay, so the gradient is 1. Yeah, so I mean, you can try all the direction, right? Directional derivative. You can check all the direction u. Okay, with the unique vector. Okay, you should find 1. Yeah, so this is the purpose of gradient, right? Either your gradient will decrease or increase, or yeah, then it will give you a different shape. For example, this gradient here is decreasing, decreasing when you go further in x. And then this gradient is increasing when you go further in x. Okay. But if you get the cone, you just have a constant gradient. Okay, no? Okay. But basically, these are the 3 types of geometry you can see in this world. Yeah. Okay. 3 types. Only 3 types. You have spherical, hyperbolic, and flat. Okay. Yeah. Okay, so we determine the cone already. We want to do. Okay, so we want to find the volume. Okay, volume bounded by this intersection here. How to find volume? 2 ways you can find volume, right? You can use double integral, or you can use triple integral. But if you want to use triple integral, you need to integrate over 1. Okay, otherwise you will get a hypervolume. Okay, so what do we want to use here? Okay. Let's use triple integral. Okay, so let's use triple integral. So what's the integration domain here? Huh? Which coordinate? Hello, morning. Huh? 嗯 Okay, so what kind of coordinate you want to use here? Spherical, rectangular, or spherical, rectangular, or cylindrical? Which one can help you to draw a sphere? Spherical. Okay, let's try and use spherical. For spherical, you have radius, okay? You have angle on the xy plane. You have another angle from the positive z-axis. So let's try to find the radius first. Which one first? Which one is easier? Okay, let's do, maybe let's fix theta first, because let's fix the angle on the xy plane. Okay, let's fix the angle on the xy plane first. So you can see that we swipe out the whole circle here. Okay, so we are taking theta from 0 to 2 pi. How about phi? How do you find this pi over 4 here? How to find the pi over 4 angle there? Sorry? Radian? So? Given that we know the slope, you want to use that. Wait, let me think. But we only check one side of that. So let's say if you check for all the direction, unit vector, you found that it's 1, then you can use that to find it. Okay. Otherwise, can you find it another way or not? So you see, what can you see here? So here, perhaps this angle is easier. See, so if you take a point down there, right? Okay, if you can, so okay, just how should I put this? Okay, so you look at the okay. First of all, we know that it is a triangle. I mean, below the cone is a triangle. Let me do like this. Okay, what's the point down there, down here? This is just some point x1, for example. Okay, but we know that this side here and this side here has the same length, right? Because for the horizontal line here, this is the distance from origin to x1. But the height we also define as this length. Okay. Okay or not? So this is what? This is an equilateral triangle. Okay or not? A right angle equilateral triangle. So it must be 90 divided by 4 for the other two angles. Equilateral triangle. 的边三角形 is this like same things, right? So you have A here, right? You have A here, right? And then you have a right angle triangle. So what's the angle here? Oh, right. Isosceles triangle, sorry. Yeah, isosceles triangle. Yes. Yeah. Say the wrong thing. Yeah, only two of them is the same. Yeah. Isosceles, yeah. Correct. Yeah. Yeah, correct. Yeah, isosceles. Yeah. Only two sides are the same. Oh, another way to find this theta is you can use tangent, right? Tangent of A over A, which is okay, tangent theta equals to A over A. So tangent theta equals to A over A. So theta equals to tangent of okay, which is powerful. Okay, does it sense or not? Okay. So the other side will be 90 minus pi over 4, and then you get pi over 4. And then this works for every direction. See, this xy actually we have a this exact xy. Okay, yeah, question. Mm. Mm. What do you mean? Oh, you mean how to find the intersection point between sphere and this cone? Okay, so okay, is it okay with this already? How to find this pi over 4? Okay, we found this pi over 4. So maybe let's keep this guy first. Okay, so the question is how to find this intersection. So can you imagine what's the intersection here? What's the picture we are having in mind? So I have a sphere in this, okay, and then I have another uh, cone. Okay, my cone is extend infinitely actually. My cone is extending infinitely. Yes. Okay. Sphere is like close, but the cone is not. Cone is can keep going. Okay. Okay. So what's the intersection here? Okay, what's the intersection here? How to find the intersection? So one thing you can do is like what we do last time, right? We just let this two equate. Intersections means what? Intersections means A intercept B means what? The point must be in A and in B. So to stay on the cone, Z have to satisfy this square root expression. Okay. So you can sub this expression into the Z inside your sphere. And then see what Sy will satisfy this kind of Z. Makes sense? Okay. So let us try. X squared plus Z squared equals Z becomes X squared plus Y plus 2 square root X squared plus X squared. Ah, yeah. Then what's this? This looks a bit horrible. Hmm. Or we can turn this two onto the other side. Okay. What is this? Sorry, plug inside. What do you mean by plug inside? Mm-hmm. Mm-hmm. Plug in Z to find the point. Solve for Z. Wait. What are you guys talking about? So you want to fix the Z? Is it? Are you trying to fix the Z? We're trying to fix a z order. Yes.
We can just directly substitute z in x squared upon 3 equals to z into and solve for z.
Wait, anything you're talking about? So
We're finding that is
Mhm.
1 over 4. Or
Why?
1 over 2. 1 over 2.
Why?
Something that
Okay, what do you mean by plug in z?
x squared plus y squared is that squared.
Sure. Okay, so you mean okay. So you mean something like this?
X squared plus y squared is that squared. The left hand side is that squared.
Ah, okay. So you mean I want to replace this again.
Yeah, so that should be 1 over 3.
Z should be one of the two. Is it clear? So let me see.
The CCS is 1 over.
So can we see this easily or not? 2 to the z. 4 to the z. 4 equal to z square. Right. Then for z square, 2z square minus 1 equal to 0. So z equals 0 or z equals to plus minus 1 over 4. Right? 1 over 2. 1 over square root 2.
All that squared.
Oh, right. Sorry. Yes. Okay. So plus minus 1 over 2. Yeah. Okay. So plus minus 1 over 2. But z is square root of some number, right? So it must be positive. Either 0 or 1 over 2. So intersect at two places. Since z has to be not negative, z is equal to 0 or z is equals to 1 over 2. Okay, so intersect the sphere at 0 and at the radius of 1 over 2, at the height of 1 over 2. Okay, do we have enough information to reconstruct this already? Yeah, 1 over 2. So that means what? That means it intersects the sphere at the meridian, right? Meridian of the sphere. Okay. Or you can imagine a cone like this, and then you attach a hemisphere. Okay. Okay. So let's come back here. So what's our phi in this case? So we have found that the angle is pi over 4. So we're going to integrate from 0 to pi over 4. For the angle from the positive z-axis. How about radius? How the radius is controlled here? So you integrate all the way from 0 to where? What's this point here? How to find this length? Okay, so let's think about what have we done now. So we have theta like this. Okay, we go around here. Okay. And we have angle from 0 to pi over 4 here. Okay, but how to draw this sphere here, or portion of the sphere? So 0 up to here, 0 up to here, 0 up to here, 0 up to here. Cos what? Mhm. Mhm. Okay, so okay, you say because. So let's recall what's the change of variable here. S equals to rho rho sine phi cos theta. Y equals to rho sine phi, and then Z equals to rho cos theta. Yeah, Z is rho cos phi. Okay, so wait, so how do you get this? How? So okay, first of all, so zero, the rho here is bounded below by 0, bounded above by this sphere here. Right? 0 all the way up to the sphere. Okay, so how do you find it? Yeah, cos phi. How do you find cos phi? Yeah, yeah, yeah. So this one I put the wrong theta, right? This one should be phi. Okay, so what's this sphere in terms of a spherical coordinate? How do you write this equation in the spherical coordinate? So x squared plus y squared x squared equals z. Okay, how to turn this sphere into a spherical coordinate? So you substitute all the change of variable here equation. So what is x squared plus y squared plus z squared here? Okay, z. So here says what? This sphere will satisfy the equation of rho equals to cos phi. So you can use this rho equal to cos phi to draw the sphere now. Okay. So you are bounded above by this sphere here. Okay, so your radius is going from 0 all the way to the sphere, which is cos phi. Okay, okay. So here is cos phi. Okay, so as I said last time, the hardest part is to determine the integration domain. Okay, after you determine the integration domain, you just do the triple integral. So let's move all these things away. Okay, so let's look at this. So the triple integral we consider here is integrating over 1, okay, dv respect to. Okay, since rho is dependent on phi, we want to put it all the way inside. So with the d rho d theta or d phi first, and then d theta. Okay, so rho is going from 0 to cos phi, and then phi is going from 0 to power 4, and then theta is going from 0 to 2 pi. Okay. But remember that when you swap from rectangular coordinate to spherical, you need to induce a Jacobian. Okay, to introduce a Jacobian. So what's the Jacobian for this spherical coordinate? Rho square sine phi. Okay, rho square sine phi. Okay, okay, good. So you can go and integrate this. What do we get? Respect to rho first. So rho square, right? So rho square integrating rho square get rho cube over 3. 0 to cos phi d theta d phi. So in this case here, you will get 3 cos cube 5 sine phi d theta d phi. Okay, so you can see that now the expression is everything in phi and nothing in theta. Okay, so you can think of a constant function 1 on theta, and then you can split this iterated integral here. Okay, so we can split like this. And then, what am I doing here is power 4 from 4 over 3 sine theta. Okay. Yeah. Okay, can you integrate cos theta 5 sine phi? Do you remember how to integrate it? Then, and then integration by part, substitution. Mm, mm. Okay, so integration by substitution. Okay, the integration by substitution, what do you get? Minus cos 4 pi. Then you get Albert. Okay, yeah, so you use, so what you use here is integration by substitution. Let u equals to cos. so that your du is equals to minus sine. Okay, and then you change it back again. But one thing I want to remind you is when you do this substitution, right, make sure your integration domain is the domain where the substitution here is 1-to-1. Okay, any question on this part here? No. No. Okay. Let's maybe go through one more quickly. Okay, how about this one? Find the volume of the tetrahedron bounded by 1, 2, 3, 4, 4 planes here. X plus y, 2y plus z equals 2, x equals to 2y, x equals 0, z equals 0. So actually there are two slanted planes here. Okay, so there are two slanted planes here with different normal vector. Okay, how do you find the plane? You need a normal vector. And then two vertical. One vertical and one horizontal plane. Okay. S equals 0 is the which plane? ZY plane, correct. So it's this vertical plane here. And then Z equals 0 is the horizontal plane. Your height is 0. We bound this tetrahedron. Okay. So first of all, you might want to find all these vertexes. Okay, to find all these vertexes, you just find the solve the system of linear equation. Okay, where they intersect. Okay. So if you want to find the triple integral, right? So I need to define the integration domain first. So similarly, if you want to use triple integral to find a volume, you should integrate over 1. Okay, you should integrate over 1. Otherwise, you'll get something higher dimensional. Okay. So now we need to determine what's E here. Okay, how to see? Say, let's see. Say we want to determine function of dx, dy, and dz. So we fix x, y, z first. Okay, let's fix x first. Let's say we already find all these integration domains here. Okay, I mean all the intersection here. So what's the range for your x? 2, 1. Okay, so 0 to 1. How about y? Very trickier, you see. So if you fix x here, right? If you fix the x, you can see that the y is bounded below by this line here, and bounded above by the other line. I mean, this line is x over 2 from the plane here, right? So here, this line here is what? Here is y equals to x over 2. How about this line? This line here lies on this plane, right? But it is on another plane again. So z equals 0. So what do you get in this case? You get x plus 2y plus 0 equals to 2. Okay, no? Okay, so this line is actually what? Y equals to 2 minus x over 2. Okay, so it's bounded below by x over 2 and bounded above by 1 minus x over 2. Okay, no? Okay. Okay, now we have determined this domain here. Okay, R2 domain here. So we need to determine this height. So given a point in the xy plane, okay, how does the height changes? Okay, how does the height changes? So you can see that they all start from 0. Okay, they all start from 0. Okay, how about the upper limit here? It's for the point at 0, 0, right? But away from 0, 0, the height change. So it depends on x and y, depend where you stand. Okay, it depends on where you stand. So you use this plane here. So here tells you that z is equals to 2 minus x minus 2y. Okay, yeah. So this height here is bounded above by the plane 2 minus x minus 2y. Okay. Makes sense or not? Okay. Yeah. So you can do this integral here. Okay, you can do this integral. So you can try other method, right? For example, swap this order here. Okay, you can swap the order. Y x z, z x y, and then see how this integration domain change. Okay. Can or not? Okay. But actually, this question also can be solved using double integral. Okay, how to solve using double integral? Which function you want to integrate over? Or you can do double integral. Then what's the function you can use here if you want to do double integral? X minus 2y. Okay, so you are using the area under the, no area, the volume under the plane, 2 minus x minus 2y. Okay, and then you integrate over the domain here below here. So you need to find this triangle domain here. Okay. Okay. So what's this domain here? This domain here is exactly what we have found just now. Yeah. Okay. So this domain here is what exactly we have found just now. So we're integrating x from 0 to 1, y from x squared to 1 minus x squared, x minus 2y of dy dx. Okay, now can you see that this two actually is the same thing? So maybe I expand the triple integral out. I'll get 0 to 1 and then uh, x over 2 to 1 minus x over 2. And then on the z direction, we have 0 to 2 minus x minus 2y, integrating over 1. Okay? And then dz, dy, dx. Then the z component here will just give you 2 minus x minus 2y. Okay? So this is a generalization, okay, of double integral. Okay, so that's why in the assignment, right, I find the Gaussian integral using double integral, and then I ask you go to triple integral. Okay, when you go to triple integral, you can extend it in this way, easier way, or you can use harder way like spherical way. Yeah, all of them will work. Okay. Okay. Yeah. Yeah. Any question before we take a break? Or you want to see one more? Maybe let's try last one because I prepared it. Okay, this one. Let's say if I just give you this integral here, right? Can you draw the diagram here? Okay. How can you turn this integration domain to a picture like this? So let's try and list down the integration domain. What's the order here? So you fix x first, and then y, and then z. Okay. X is going from -2 to 2. Okay. And then y is going from square root 4 minus x squared to minus square root 4 minus x squared. And then z is going from square root x squared plus y squared up to 2. Okay. So you should start with drawing the first interval first. Right? So you start with drawing x. So x is going from -2 to 2. Okay. How about y? Does this looks familiar or not? What is this? Y equals to 4 minus x squared, square root 4 minus x squared. This is a circle. Okay, circle with radius 2, center at 0. Okay, so it is actually this part here. So here is the y equals to so here is the y equals to square root 4 minus x squared. Change the sign. So bottom here is the square root 4 minus x squared. Okay? Okay. Okay. And then z. What happened to z again? Z is bounded below by this length function again. So we call this a length function. This is like a norm. Okay. This is a length function and then bounded above by 2. Okay. So it's similar to what we have just now. It's a cone. Right? Bounded below by a cone. Bounded above by a plane. Z equals 2. So instead of getting the hemisphere just now, we just cut it flat. We just cut it flat. So we get exactly this cone here. A finite cone. Okay. Okay. Yeah. So what kind of coordinate is suitable for this? Hmm? What kind of coordinate is suitable for this shape? Cylindrical. Okay. So when you think of which coordinate to use, you should think of, can I cut this shape from a sphere or not? Can I cut this shape from a cylinder or not? Or can I cut this shape from a rectangle or not? Okay, rectangular box. Okay, so one easiest way is you cut this shape from a cylinder. Okay, so if I change this to a cylindrical coordinate, what do I get actually? So let's call this shape here E. So what is E in a cylindrical shape? We have rho, theta, and the Z and the height. Okay. So rho here is the radius. Okay. So radius of this shape is 2. Right? So all the way from 0 up to 2. And then it is in a radial direction, all the way from 0 to 2 pi. How about Z? So it is bounded below by 0 and bounded above by 2. Okay. Let me see. Bounded below by what? Not 2, not 0, right? If bounded below by 0, I should get this cylinder. So I need to cut by this cone here. What's this cone in a cylindrical mode? So it is Z equals to square root rho squared, which is rho. So bounded below by. Okay. Then you can do the triple integral. Can you find this using spherical or not? Can do this in spherical way or not? Need to do the plane. Need to do the plane. Right. Need to do the plane. So maybe use another color. So let's use this for spherical. So this plane in spherical can be described or not? So it is rho cos phi equals to 2. So the rho here becomes what? 2 over cos phi. Okay. So if you're going to use spherical, then your radius will be bounded above by 2 over cos phi. And then the theta is the same, 0 to 2 pi. Okay. You swipe out the whole circle here. Right. And then your phi just now we found already, right? This phi is pi over 4. Okay. Okay. So I challenge you. You can try and do this. And then you can let me know what you get. Okay. You can send me to check. So I can pick rho from 0 up to 2 over cos phi. And then theta going from 0 to 2 pi also. And then phi going from 0 to pi over 4. Okay? And then you should get the same answer. You can try it. And let me know. Okay. Does it make sense? So if you use different integration domain here, you should use different Jacobian in your calculation. Okay. Okay. Yeah. If you try, you let me know. Okay. Of course, you also can do the rectangular calculation, right? But you see, there's a lot of square root square involved. So you should do some trigo substitution. So what does trigo substitution mean? Meaning you change coordinate. So actually you change to spherical or cylindrical. Eventually you lies between these two, one of these two. Okay? Yeah. So when you do trigo substitution before, it means you change coordinate. Okay, change to spherical or cylindrical. Okay. Okay, any question about this? In next hour, we should start new chapter. Any more question on the double integral stuff? Multiple integral. Okay, so if you can, when you do one question, right, try as many order as you can, so that you can see an object from different direction. You dissect the object from different direction. Okay, and then test your skill whether you can determine the integration domain or not. How to find different interval, okay, for your variables. Okay. Okay. Any question? Yeah. Mm. 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 This one. Mm. Mm. Other below by row. Row. Okay. Mm-hmm. Yeah. Mm. Mm-hmm.
I don't just order by 0.
You don't just bound by 0. Yeah. Okay, good. So why you don't just bound by 0? So what is that? Z is the height, right? Is the height. Okay. If you bounded by 0 means what? For every point on the circle here, okay, because we start with a circle, radius 2 and theta from 0 to 2 pi. If we bounded by 0, meaning what? I take all the way from 0 to 2. So I take the whole cylinder actually. It's not a cone anymore. But I don't want anything below this cone. So meaning what? This point on my cone here is bounded below by the surface of the cone. So what's give you the surface of the cone? It is exactly the function z equals to square root s squared plus y squared. And then what is s square root s squared plus y squared in terms of cylindrical coordinate? It is actually rho squared plus y squared. Sorry. Also, it's rho squared. Rho squared. So square root rho squared, you get rho. Okay, so the height is equals to the rho. Makes sense, right? Just now, as what we said just now. How we get this cone? It is the height of the length of your point. Rho is what? Is the radius. So it is the length of your point. Radius is counted from origin to the point, which is the length of your point. Makes sense? Yeah? Mm-hmm. Correct. Mm-hmm. Correct. Yeah, yeah, you can. You can. Yes, you can. You can. Well, which one you want to do now? So you want to do dz. So you want, okay, so you want to try and work with different order in cylindrical mode, is it? Okay, so let's try. So here is E1, here is E2 maybe. So you want to fix Z first and then maybe theta rho and theta. Theta won't change. So only rho will depend on the Z. So Z going from where to where? Z is going from 0 to 2, 2, correct. Okay. How about rho? So how does the radius here change? Okay, so if you have, so you should imagine Z is in this direction here. Okay, you fix one Z. How does this radius change? Okay, you fix the Z. Okay, how does this radius change? So you can see that the Z at the top here, the radius here is, what's this? The radius here is 2. And then when the z decreases, the radius also decreases. Okay. So it is bounded below by what? Obviously, it's bounded by 0. You should think of how this radius interval change. So radius interval is going from the origin. So you should start from origin. So you can see that at every height here, you include origin. Make sense? Okay. But the radius here decreases when you go down. Okay. So it is bounded below by 0. Okay, bounded above by what? You can see that when the z decrease, the radius decrease. So how the range? What's the rate? The cone equation is the rate is z equals to radius. So the radius will change with the height. So rho is bounded below by your height. Yeah. Okay, and then theta is going from 0 to 2 pi. Okay, so you can see what happened here. So you can see that this z equals to rho happened in different endpoints. If you do different order. If you do the order z rho theta, it becomes the upper limit. Okay, but if you see from rho theta z, so if you see from how should I put this? So if you see from xy plane perspective here, you can see that your z, your height, okay, your height is bounded below by this cone. Okay, depend on how you see the shape. Okay. And then the cone here will serve as an upper limit or a lower limit. So this cone here serves as an upper limit for your radius. Because if you want to extend radially, right, you can only meet the cone as far as z, yes. But if you want to extend in height, okay, you cannot touch lower than the cone. You cannot go lower than the cone. You cannot go lower than the cone. Okay, I don't want anything below the cone. Make sense or not? Before we take a okay, so if you go in radial direction, you cannot go outside the cone. If you go downward in z direction, you cannot go outside the cone. So if you increase in radius, you cannot go outside the cone. If you decrease in height, you cannot go lower than. Okay. So that's why one of them is the upper limit, the other one is the lower limit. Okay or not? Jason? Okay. Yeah. And where is strange? Which part is strange? You see? Okay, let's take a break until 10:32.
我想是哪里？
对啊，
我那外地人有一个，当初是2说，我去跟他们讲，公司的，现在对，为什么这里我要学一下？为什么的空间因为基本大部分的是那种，如果刷你大部分是我已经在上播了。那如果大部分的对上面就讲，就是大部分的就是在什么？就是他算 OK，算第一个那个 first 那个 one，你看那个 area 的组合，所以如果你去说的话，你对它有第对，你就上到第四，所以我所以你现在下到没有，所以你这个所以你结果是对，我上次说那个嘛，就是你的那个 box volume of life。你如果有一个 rectangular 的 line，可以产生很高。就已经有了。如果你的 text 这样的话，这 volume of 这个 box 分你的 area，那个 base area，所以你把它这样子后，可是我整个都把它这样放到对的。你这个有啊，你还不是？是因为本来讲平面。这个企业嘛，因为要求要总结来说，我这个是进的。啊，天都不要去给上进，那我们是这么。就是随便点点进去，这个点啊，不是他们打他那个126嘛，来变成90度，没有，然后那个变可以，但是你就要证明你刚才之前所说的。你要证明你刚才前面所说的东西哦。哎，那个什么前面？对呀，对呀，对呀，为什么我是点外的？对呀，如果你给我讲完全部东西，因为你有不同的知识。反正是我们以前学的时候也没有说为什么去那种两法就行。我这二什么时候交啊？今天下午。今天下午交二特，下午就可以是，因为现在没有什么人，今天下午才是个。换到打低位啊，对呀，他不周，那不就是下周啊？要不换到 final week 吧？一个很好吃的，打低位的话，应该来买。哦，我呀，我们有，我们这边应该有。两个月，大概是6个月。讲嘛，那星期那因为哦，我第一因他用的是现在因为那星期1月3对不对？星期7所以你们要在这个之前写完，在这个之后，星期5好，但是你还没有显示到，好，该放葡萄成熟吃了，还好吗？这个葡萄成熟吃了，差不多，我妈的天。广州人的信仰，对，为什么？因为每年一到过年的时候会把刘德华那个把这个会爬去广州，对，流浪的，他说有山 一直在讲今天这个课不怎么课。
对，哦，我昨天看了，前天，
我礼拜二要再看点，到礼拜日还没有上课，我礼拜二在上的课。
哎，最近那个你的那个某人没有发邮件了，发邮件提醒了。
非常
为什么嘞？
非常差劲。
你好像又有了嘞，
哪有 bug 吧？
什么有 bug？
我不知道那个步骤。
维修到变烂，它就不能够洗出。
维修之后只能跑去这个程度。
先讲
不能，不能，你不能只看它吧，你要看一开始的包，你要看它一开始的包，你不能只看一个书跟你说，但是不太只是这个样，所以还需要
对他昨天还以为是他觉
哦，就是没有。啊，对，因为它没有 match 它是不能的，所以其实只有两种可能，只要就换的那个也就是这就是两种时间吧，没有办法。上过6个小时啊，你串在一起了，
连上了，
也是这样休闲的。
所以基本可以。
哦，你点就反一的，这样
一学期
一门也是不可能。
我们今天参加234
啊，
下午还有一个实验小组，就显示你在打网不是很重要。
就会人口
非常恐怖，但是不是
行。OK，
那你有去吃
现在是
要跟我们讲
午餐还是什么？
午餐？
可以啊，可以啊。
因为有
virtual 啊，virtual metaverse。
广州感动没有打卡在广州。机票，我们下个月你要1周，
可以可以
做10公。
OK，可以可以可以。
米饭对吧
OK 啊。
我现在给他对子
1、2、3、4、5、6、7。OK。Okay. Remember what we last time we talked about vector field. So this is the last variation of function we'll talk about. This is the function from Rn to Rn. Okay, we don't consider different. We don't consider Rn to Rn for different m and n. Okay, we only consider Rn to Rn here. Okay, so if you want to go Rn to Rn, you can take differential manifold. Okay, so meaning what? I give you a point in Rn, I give you a vector in Rn here. Okay, so the n we will look at is just R2 to R2 or R3 to R3. Okay, our dimensions stop at 3. Our dimensions stop at 3. So how you should imagine this physically when you do integral later? So you should think that, for example, in R2, okay, or in Rn, I give you a point in Rn. Okay, for example, here, R3. I give you a point in R3. You should imagine there's another vector R3 pointing out. Okay, f of this point. I give you another vector. So why we need this? This is like pretty much like an attraction or repulsion force. Okay. Okay, no. Attraction or repulsion force. Okay. For example, if you have two magnet together, right? So if you think of a south pole and a north pole, okay, you put them close, they will attract. They'll attract, right? So how to think of attraction in mathematics? You can think of the arrow pointing inward the pole. Okay, so let me draw. So maybe you have this N, and then you have another one S. Okay, and then if what they want to attract, you can think of the force is like coming in. Okay, look. Okay, and then if you put the same pole together, they want to attract. They want to. So you can think of the forces going outward. Okay, is it correct? Does it make sense? So have to go out. Okay, yeah. Let me think. From M to X. Okay. So you mean you fix one direction for, wait, I don't want to erase first. So you mean you fix one direction for the force, is it? Okay. So we fix one direction for the force. For the pole. Okay. So this one go in, then this one will go up. So you up, you in, then it will fill out the space. And on to here. Okay, so you can think of this for each point, I will attach a vector. Okay, for each point, I will attach a vector. Each point, I will attach a vector. Arrow. Okay, for each dot, I will attach a arrow. Okay, so this is the vector field. So why they call it a field? It's like you imagine you are on the playing field or a running field. Okay, and then on the field, every point you have a vector. So that field is a different field from the mathematics. There's another field in mathematics. Okay. Have we motivated enough? Yeah. All right. So what is vector fields on R2? So we have a D, a set in R2. Okay. A vector field is a function. Okay, it's a function. Remember, it's a function. So in mathematics, right, there are typically only two main things: either set or either function. Okay. Either set, either function. So vector field is a function. So function from where to where? So function, if it is vector field on R2, is a function that assign every point x, y in your set D, okay, a two-dimensional vector. Okay, give you a two-dimensional vector. So similarly, you can extend this idea to R3. So for every point in R3, I can assign a vector in R3. Okay, for example, the gravity. Okay, gravity is a can be realized as a vector field in R3. So I pull towards the center, the mass. Okay, so let's try and compute this. So I give you a function, okay, from R2 to R2. So this is the vector field, okay, and then try and find the value of the vector field on this point. Okay, so there's a subtlety here. There's subtlety here. So what do I mean by subtlety? You can see that on the right hand side here, I don't put ij, but on the left hand side here, I don't put ij, but on the right hand side here, I put ij. Why? But they are all points in the xy, right? And the R2, I mean. Okay. So on the left hand side, I emphasize the xy as a point. Okay. On the right hand side here, I emphasize the point in R2 as a vector. Okay. Both of them are elements in R2. Okay. But one of them I emphasize as a point, the other I emphasize as a vector. Point is just some location. But if I say vector, I want the magnitude and the direction. Okay. Point is just a location. Okay, so try and find for each point here, find the corresponding vector given by the vector field. Okay, if you can, try and plot it out. Okay, and then you should keep this example in your mind, like whenever you see vector field later. So this is a prototype for a vector field. I give you 5 minutes, try and count all of them and then plot it. You have to try this, otherwise later you will get lost. You don't know what you are interpreting. Okay. Finish calculation or not? Okay, so what's the point? What's the vector on 1, 0? J. Or maybe I put 0, 1. Okay, how about 2, 2? What's the vector on 2, 2? 2. And then next one, 0, 3. And then minus 1, 0. Minus 1, minus 2. Minus 3, 0. 0, minus 1. 2, minus 2. 0, 3. 0, minus 3. Is it? Yeah, the previous one. Let me check. Should it be 0, minus 3? Yeah, okay, 0, minus 3. Okay, next. 0, 2, 2, and 3, 0. Okay, so how do you plot this? Maybe we see from this 4 points first. Which 4 points? So let's look at 1, 0, 0, 1, minus 1, 0, and 0, minus 1. Okay, why do I pick this 4 point here? These 4 points are living on the same circle. Okay, these are all length 1 from the origin. So in particular, here is 1, 0, 0, 1, and then minus 1, 0, and then 0, minus 1. Okay, so at 1, 0, what's this vector here? 0, 1. So there's only direction in the y direction going up. Okay, so you have a vector going up. Okay, here 0, 1. How about at the point 0, 1? The vector is going to the horizontal direction, going to the left. Okay, so I have going to minus 1, 0. Next, going downward at minus 1, 0, because you have a y direction which is a negative. And then at 0, minus 1, you have 1, 0. So what does this do? So you can think of this vector field is like rotating the circle. Okay, similarly, you can plot all these, okay, and then you will get this kind of shape here. Okay, so this vector field is like rotating the plane. Okay, so you can imagine if I put a particle here, okay, then this particle will flow with your vector field. Okay, so you can think of a particle get pushed by all this arrow here. And then the particle will flow with this arrow and then rotate around the origin. Okay, does it make sense? Okay, now. So whenever I say a vector field, you should think of this vector field is like flowing in a plane. Okay, flowing. And you can think of a current flowing or something, or water flowing, or the wind current or something, wind blowing. Makes sense? Okay, this is what you should think of vector field when I first tell you the word. Okay, next example is something like this. So you can think of this force or vector pointing outwards all the way, right, in the R2 dimension. So this is the formula I gave here. So what is this square root x squared plus y squared again? I pop up again. This is the norm function. Okay, so it means that at every point, the arrow not only outward, the magnitude is depending on the not depending on the depth. Actually, I divide by the length of my vector. Okay, so meaning I have a unique length at each point. Okay, so I normalize the vector. Okay, no? Okay, I normalize the vector. Okay, so similarly, what can we do? We can extend this result to gravity. Okay, so we will have a gravitational force field, for example, here. Okay. The GLM over R squared. Yeah. So here there's a minus sign here compared to what we had before because this is going inward, just now going outward. And then why we have an R cube, why we have an R here? Because we don't just care about the scalar number, I care about the vector. Okay. Okay. So these are just examples. You can try and derive it, but it's okay. You just try and learn how to compute this vector integration on vector field or differentiation. Okay, so next we'll define what's called a gradient of a vector field, a scalar field. So let F be a scalar field. So what's a scalar field means here? So vector field, the output is vector. Scalar field, the output is scalar. Okay, so here R is a map from Rn. Okay. And suppose F is a differentiable. So this type of function is what we had before. Okay, we define the surface, right? It's using R2 to R or R3 to R. Okay, and then the R will tell you the height of each point. Remember, not the level curve. Okay, so the gradient of F is what? Actually, is a vector field. Remember last time we calculate the gradient. What's the definition of gradient again? Anyone remember? Ah, there's something related to the change. Du f equals to what? Directional derivative of f equals to what? Fx comma fy dot product with the unit vector uv. Okay, so let's call it u1, u2. Yeah. Okay, where u equals to u1, u2, and then the length of u is 1. Right, so you see, we define the del f to be the vector fx, fy. So what is del f in this case? What is del? What does del do? I fit in a function, give me a vector here, right? So what? So what is this vector here? I can evaluate my gradient at fxy, and then I can also evaluate the vector in x1. Meaning what? I fit xy into del f, it gives me a vector. So this is exactly a vector field. Okay. So now we see the gradient of a scalar field as a vector field. Okay, we use different language now. It's the same thing, but we use a different language. Okay, so for example, find the gradient vector field of this fxy equals to s squared y minus y cubed. So this is a map. So this f is from where to where? From R2 to R. Okay, so in particular, this is a scalar field. Okay, so for a scalar field, I can find the gradient. Okay, so what's the gradient of f here? Del f. And what's del f? 2 y minus comma minus 3y, sorry, s squared minus 3y squared. Okay, so what's this formula here? Right, so this is really del f del x comma del f del y. Okay, okay now. Okay, but the point in here is del f is a function from R2 to R2. Okay, right? So for example, I feed let's say 2, 1 into my gradient function here. I should what vector I get? 4, 1. Yes, 4, 1. Okay, so it's a vector field. Okay. So we see gradient of a function, a scalar field as a vector field. Remember just now what we did? Each point, okay, attach a vector to every point. Yeah, amazing. This is just a language yet. We haven't introduced much property. So one property we want to introduce is a conservative vector field. Okay, what does it mean by a conservative vector field? So a vector field. So you see, so here, how do you start? How do you split out language here? So you should see that conservative is an adjective. Vector field is a nouns. So meaning I know vector field already. I just don't know what is conservative vector field. So meaning you should tell me if I give you a vector field, how do you decide if or not? Okay. So the definition starts like this. A vector field F, okay, that is the gradient of a scalar function is called a conservative vector field. Okay. So it means what? If your F is coming from a gradient of a scalar function. If then the capital F is a conservative vector field. Okay. Okay. And then we also have another name for this kind of F. We call it a potential function of the vector field. Okay. So if you can show that your vector field is a gradient of some scalar field, and then we will call this vector field conservative. Okay. At the same time, we will call the little f as the potential function for the vector field. Make sense? Okay. We will use this language later on. Okay. So it says that the remark here says that not all vector fields are conservative. Meaning what? Not all. So you need to use contrapositive of this statement. No? Not all vector fields are gradient of some scalar field. Okay. Make sense? Okay. Not all vector field you can realize as a gradient of some scalar field. Meaning you cannot just take any scalar field that and then do the partial differentiation. Okay. And then to get the vector field. For example, let's show that this gravitational force field is conservative. Okay. How to show this? You need to show that it is a gradient of some scalar field. Okay, so which scalar field you have to pick? The question gives you the hint already. Take this one. So try and take the gradient of this scalar field. Can you get this vector field now? Okay, try and compute this. Okay, try and compute this. Can you see that we have a combine all the constant here become just a C? Okay, we don't care about the constant here for now. We just care about the direction. Okay, try and see if it is true that the gradient of this potential function is the vector field. You try and compute it. So what we want to show here? So we want to show that F is a conservative vector field. That is F equals to del theta F for some scalar field F. You just need to find one f, okay, and then the question gives you the f already. So you can just try and verify it. Yeah. Should differentiate this potential function with respect to three direction. Okay, what do you get? This three direction should give you the same pattern. So for the first one, what do you get, Jingsen? X 2x, okay, yeah, 2x over 2x over 2xc, okay, over square root x squared. Is enough? You sure? Not quite sure. Okay, so I mean, if you are not quite sure, maybe I prefer to integrate in this kind of lead, okay, in the indexes form like this. Then you will know what kind of a chain rule is involved, right? So how do you integrate, differentiate this, right? So you need to differentiate the whole expression, okay, and then do the chain rule inside. Okay, so the chain rule inside will give you the 2x. Okay, but if you try to integrate the whole expression, you need to decrease the power of, which is minus 1 over 2, because it was negative before. If you decrease by 1, you should get square root 2. Yeah, which form do you like? Okay, they like this form. So let's do this form. X squared y squared plus z squared times 3 over 2. Right. Okay. And then you need to bring the power down, right? Okay, so you should get minus of. And this is fun. Okay. Okay or no? Okay. Yeah. So similarly, you get the same across. Okay, should I? Okay, let's write it out. So I just get 2yc in this case. And then this side I get over x squared. Okay, does that make sense? Make sense or not? Okay, so you can see that you will get the same answer. So you get xc over x squared plus y squared plus z squared to the power 3 over 2. And yc minus, so we still have a minus sign. That c also over x squared plus y squared. Okay, yeah. So it's exactly the vector field you want to find here. So minus c times x in the x direction plus y in the y direction plus z in the z direction. divided by the length of your point. Okay, length of your point to the to the to the so you have your length of the point, right? And then you have to cube it. Yeah, you take the cube of your length of your point. Okay. So what I mean is this is equal to xi plus yi plus zk over x squared plus y squared plus z squared to the half to the 2. Okay, no. Okay. Later on, we will have a lot of things involved this conservative vector field. Okay, any question before we go to the next part? Okay, no. Can later we'll involve integral with this conservative vector field. Okay, it's not question. Can we take a shorter break? Let's break until 11 and then we'll start. Okay. Is that any question? Before we start. Okay. Okay, can we continue? Okay, let's continue. Okay, so again, from your calculus one, right? Okay, we can compute the area under the curve. Okay, we can compute the area under the curve like this. Okay. What if I extend the dimension? Okay, I extend the dimension. I extend the dimension like this. Okay, I extend an extra dimension on my domain. And then I let my curve run in the R3 dimension. Okay, you don't just run in a straight line anymore. You run in a different direction. Okay. Can I still find the area under this curve or not? Okay, can I find the area under this curve or not? Okay. The answer is yes. Okay, and then this is what we call the line integral. Okay. We are integrate over a line. Okay, so we call this like a curtain. Is it a curtain? Is it a curtain? Is very so what is so? It's like wavy, right? It's like curvy, right? Wavy. So it's like you need to wave in a 3D space, right? Okay, you cannot wave in 2D space. You cannot see the wave. You see? You cannot see the wave here. But in 3D, I can put wave like this. Okay, and then the area under the line will become the something like a curtain. Okay, so how to do this? How to do this line integral? Okay, first of all, so line integral here in calculus 1, it is only one variable you need to integrate over. So can you describe the curve using one variable or not? Can you do that? What is that? That's the parametric equation. Okay, you use the parametric equation to turn this curve into a one variable thing. So I need to describe. Let's see, be a smooth plane curve. Okay, or last time we call it a space curve, right? Space curve, plane curve. Okay, defined by x equals to xt and y equals to yt. Okay, let's say we fix a finite interval. Okay. So how do we define this line integral here? Okay, so the line integral over C. Okay, line integral of a function f. Okay, so let's say this function is fxy over C. Okay, over C. So where is my C? So C maybe is below here. Okay, C is below here. So maybe we pick a bit curvy C here. So maybe like this. Okay, over C is integral over C fxy of dx. Okay. So you see that this x here is not straight. Okay, something is not straight. How do we compute it? Remember how we compute the arc length? How we use the Pythagoras theorem last time? Okay, how to compute? How to estimate? Okay, how to estimate the line, the arc length of a curved line, right? So we pick 2 points here, and then we find the hypotenuse, and then when we cut more and more points, okay, this hypotenuse will approximate the original length. Okay, so what we have used last time is actually the square root of x prime t. Okay, so the linearized version, okay, of our curve x prime t plus y prime t square. Okay, so the difference from last time is we just have this as our arc length. Okay, but now we have a height. Okay, but now we have a height here. We need to consider the height. Our height will change above the t. So last time when we compute the arc length, right, we just put the function f as a height 1. Okay, so the area under the line integral is the same as the line. It's how we do integration just now. How we do volume of a tetrahedron just now. Is a tetrahedron? Yeah, volume of a tetrahedron. We can do triple integral, but over a constant function 1. Okay, so although this integral here compute the area, if I put height 1 here, I just get the length actually. Okay, but now when we do for general line integral, we can change the height. Okay, we can change the height. So we change the height function at every point, which is f as t. Okay, yeah. So this is the line integral. Line integral we have to do. Okay, so let's look at one example here. Okay, just skip all these. Okay, so the actual definition is still the limit. You can read about it, but not very important here. Should we do this? Control. Just throw. Okay, let's see. What example is different? Maybe let's throw this one. Okay, let's do this one first. So try and do the line integral of the function x. And what is the line integral here? We want to integrate c, which is made out of c1 and c2. So what is c1 and c2 here? So c1 here is the parabola. Okay, y equals to x squared from 0, 0 to 1, 1. And then followed by a vertical line here. Okay, so meaning what? So what is 2x? What is 2x here? 2x here is a plane. Correct? It's a plane. Okay, with the normal vector 2, 0, 0. Correct? Okay. Oh, sorry, not 2, 0, 0. So the plane is z equals to 2x. So the normal vector here should be 2, 0, and minus 1. Okay, so you should think of an plane up at the top here. So what's this plane? So 2 is which side? 2 is this side, 0 is this side, and then minus 1 is down there. So you have a plane going, going like this. And think about it. And you think about it. Yeah. Okay, and then you want to find what is above this line here. Okay, you want to find what is above this line. Yeah. Right. Okay, so what should we do? So first we need to parameterize this curve first. Okay, so it is spread into 2 parts. Okay, so spreading into 2 parts, right? So we need to have additive property. We need to have an additive property, additivity line integral here. So that's easier for us to do the calculation. So we can really split the integral into 2 parts. Okay. So what is additive property here? So if a piecewise smooth curve C is made up by joining finite number of smooth curve. So do you know what a smooth curve means? You can differentiate infinitely many times. Okay, yeah, you can differentiate infinitely many times. You can keep differentiating the function. Okay, it's smooth. joining a finite number of smooth curves, then the integral over c, okay, f dx is equal to the integral over c1 plus integral over c2 plus all the way up to integral of c. Okay, so for example here, our c is made out of two smooth curve. Okay, so we can split the integral of c. Okay, so integral of c 2x dx into integral over c1 2x dx plus integral over c2 2x dx. Okay. Yeah. Okay. And then so we need the parametric equation now. Okay. So what's the parametric equation now? So what is the how do you describe C1? How you describe C2 here? Okay. So you need to tell me what is ST, right? What is ST? What is YT? Okay. What is ST? What is YT? So what? So in C1, the point follow the curve y equals to x squared. So if ST equals to t, YT have to be equals to t squared. Okay. And then what's the, so you see, now, just now I tell you where's the starting point and the end point, right? Now you need to turn this starting point and end point in the two-dimensional space into time variable, only one dimension. So I tell you, time 0, where am I? Time 1, where am I? Okay, so I need to go from the position back to time. Okay, so at 0, 0, where's my time? What's my time at 0.00? 0. Okay, and then at 1, 1, where's my time? My time is 1. Okay, so the interval is going from 0 to 1. Yeah, no? Okay, and then how about C2? C2 is a vertical line. Okay, it's a vertical line. So meaning what? S is a constant function 1. Okay. How about Y? Y, you can let it depend on T. Okay. In this case here, T is going from where to where? Okay. Yeah. Of course, maybe you will ask the question, maybe you are very curious. Can I put T square or not? Okay. You can. That one is just different parameterization. And then you will see that you will cancel in the formula. Because in the formula, we will need the square root s prime t plus y prime t. So the derivative will take into consideration inside my integral. They will somehow have a cancelling effect. Because that's how the arc length works. Okay. Let's go on, not go into deep first. Let's compute this definition, this calculation, and then you can experiment yourself. Okay. So let's take this parametric equation. So let's try and do the computation here. So what's the formula? Let's say for C1, okay, we are integrating from 0 to 1, okay. F evaluated at STYT. So here S is T, so become 2T. And then square root of what? Square root of S prime T squared. Okay, so we need S prime T as well. And we also need Y prime T as well. Okay, so it's 1 squared plus 2T squared and then dt. Okay, plus Another one is going from 1 to 2. 2x, so here becomes 2 times 1. Okay. Square root of s prime t is what? 0. Y prime t is 1. Okay, so 0 plus 1 squared. Okay, so what am I doing? So I'm actually, what am I doing? So I'm telling you that what happened on C1, what my function becomes. Okay, on C1, my function become 2t. On C2, my function become constant 2. Okay, so this is what the substitution is doing. My function changes, you see. Just now I integrate to x, right? Okay. But you can see that on C1, my function depend on t. But on C2, my function become a constant function. Okay. 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 And then there's a contribution from your arc length. Then try and do this integral here. Okay. So what's this integral here? I think you use the integration by substitution. So you use integration by substitution. Yeah. So first integral, you use integration by substitution. So you use u equals to 1 plus 4x, 4t squared, for example. Then du equals to 8x. Sorry, mt dt. Okay, so the first one will become what? Integral from 0 to 5. Okay, and then you will get what? Okay, 1 over 4 of square root u. Okay, so square root u. I think this one is easier to calculate, right? 2t, 2t, 4t, 8, 4 minus 2, you get 2. That's where you get 2. Let's check. Yeah, I get 2. I get 2. Okay, so the first integral you should get. What should you get? Okay, so we just compute it. So this one is u over 3 over 2 over 3 over 2. Correct? Over 5 plus 2. And then this is 1 over 6 of 5 over square root of 5 minus 1. Okay. Okay. Yeah, just integrate square root u. Correct? Yeah. Plus 1, right? Integration, you need to plus 1 to the power. Yeah. Correct. 2t, correct. 2t, and then you evaluate from 1 to 2. Finish already. We finish that calculation. It's 2. Okay? Okay. Make sense or not? Okay. Compute this part actually. There's another way to compute this integral. So just now when you sub, just now I told you that this 2x here over this line is a constant function 2. Right? You see 2x. 2x of this function here is just what? It's just 2. It's just 2. Make sense or not? No. So the function 2x on C2 is just constant function 2. Can you see this on the calculation here? X is equals to 1 here. So the function f here is just, so here f equals to 2x, right? So y equals to 2x, but x is always equals to 1 here. So you always get 2 here. So if I want to compute the area under this function over this line, is what? It's just a area of a square, okay, which is 2 times 1. Yes, which is the height here is 2. The bottom here is just 1. Okay. Yeah. It's also 2. See? 2. Okay, it's the 2. Okay. Can or not? Can? Okay. Another thing you want to try if maybe you want to change different parameterization. Okay, you should get the same answer because you will change your domain also if you change different parameterization. Okay. Okay. Okay, let's go on. There's one example you can try yourself. This example here. Yeah, see? So this example will demonstrate if you use a different parameterization, you should get the same answer. Okay, so if you want to evaluate the line integral of 2 plus x squared y dx, okay, over this hemisphere, semicircle, okay, just semicircle, not hemisphere. You can describe this hemisphere in 2 ways. Okay, one, you use cos t sin t, okay, where the t go from 0 to pi. The other one you can use the circle equation, okay, where the x is going from -1 to 1, okay, -1 to 1. So if you regard this x as t, right? Okay, you can regard this x as t. Then you can see that these two t start and end with different places. Okay? But no matter how you parameterize, you should get the same line integral. Okay, so that means the line integral already take into consideration different parameterization of curve won't affect your integral. Okay. Okay. One key point is because of this extra factor here. This factor here will help you with the parameterization. See this factor here. Okay, if you change your parameterization, you can see that your derivative will change. Okay, and then it will help you compensate the different parameterization you use. And then they will get the same result, integral. So the key here is the parameterization won't affect the line integral. Okay, no matter how you parameterize it, it won't affect your line integral. Okay, so it is safe. So this is what we call well-defined. It is well-defined because every time you want to do a line integral, you need to pick a parameterization. But if I pick different parameterization, does it give me a different line integral or not? Okay, the answer is no. Okay, so that this line integral is well-defined. Okay, make sense? Okay, try and go back and compute this example. Convince yourself that if you pick a different parameterization, you will get the same answer. Okay, can or not? So you just compute line integral over these two curves. You should get the same answer. Okay, any question? Any question before we go to the next part? No? Okay. So let's go to the next part. So next, we introduce line integral with respect to x and y. Okay, with respect to x and y. So we just look at one dx, integral over dx, we just look at the x direction. Integral over dy, we just look at the y direction. Okay. You can somehow ignore this first because we don't introduce this. So what is important is this, the last part here. Okay, if you integrate over dx, you will introduce an x prime factor here. So what's the relation between the line integral just now? Okay, what's the relation between the line integral just now? So just now we have a factor of square root of what? X prime t squared plus y prime t squared. So if you just integrate over the x direction, somehow you kill the t direction. Okay, so the t direction becomes 0. So you just left with square root x prime t squared. So you have this s prime factor here. Okay, similarly for y prime, y direction, you kill the x direction. And then you left with square root y prime squared. And then you left with y prime. Does it make sense? Okay, so this is what we call a line integral with respect to x and y. So with respect to x, I kill y. With respect to y, I kill x. Okay, so let's look at this example here. Let's evaluate this integral y squared dx plus x dy. Where C1 is a line segment from -5, -3 to 0, 2. So this is C1. And then C2 is another arc like this. So we'll compute this 2 here. All right, so we need to compute these 2. So meaning we want to do line integral. Let's do one of them first. Let's do A. And we want to do A. So it just says that this is a line segment. So if you want to do line integral, you need the parametrization. Okay, so how to parameterize C1 here? So you need to tell me what is xt and what is yt. Okay, but what's the equation that x and y have to satisfy here? You know how to find it? How to find it? Y equals to mx plus c. Okay, but oh yeah, okay, y equals c intercept is given, so you just need to find the gradient now. So what's the gradient for this line? It's 5, eh? Not y1 minus y2 over x1 minus y. Okay, so you use minus 3 over 0 minus 1. So you get 1. Yeah, 1. Okay, you get 1. So the gradient is 1. So the C1 curve is y equals to ms plus c. So y equals to 1 times x plus 2. Okay, so this is the equation that line have to satisfy. But remember, this line don't have direction, right? Okay, later we'll see how this direction get introduced. Okay, so ST. So how you parameterize ST? So I just let it run like T. And then Y, it has to be run like T plus 2 because this is what the line equation has to satisfy. If I let the T run like T squared, then the Y have to run like T squared plus 2. Okay. So what's the direction here? Okay, so the T will give you the direction. T going from where to where? T going from -5 to 0. Okay. If you go from 0 to -5, then you go the other direction. Then you somehow let your time run in backward. Okay, you run it backward. Okay. Yeah. Yeah. Okay. Yeah. Okay. So this is D1. So are we ready to compute already? Yes, we're already ready to compute. So for the line integral, we need x prime t and y prime t as well. So y prime t is 1, y prime t is also 1. Okay, and then, so let's compute what is this line integral of with respect to x and y. Okay, so this one actually almost by definition, right? So this is by definition. integrate c1 of y squared dx plus over c1 of x. And whenever you see this, actually you can split them. Okay, you can split them. Okay, so what is this here? Okay, you integrate from -5 to 0. Okay, and then you evaluate y squared at yt. So you have t plus 2 squared. Okay, because it's in the x direction, you kill the y part. Okay, you left with x prime t. So there's 1. Okay, and then dt. Plus integrate from -5 to 0 again. So x is t. So you kill the x direction, you have y prime t, which is 1. And then dt. Okay. So you compute this. Or what's this? This kind of long in this calculation. A bunch of polynomial. You should get -506. Okay, no? Okay. Okay. Maybe you not happy with this time here because our time sometimes almost most of the time going from 0 to 1, right? So can you parameterize such that this time is going from 0 to 1 or not? T plus 5. T plus 5. One parameterization you can make is so let me put it here. So C1 prime, okay? You can try xt equals to -5 plus 5t, and then yt equals to -3 plus 5t. Okay, wait, let me see. So as a 5t, am I correct? So if I put 0 here, yeah, and then if I put 1 in, yeah, correct. Okay, I use this. Okay, do you know how to find this? Do you know how to find this? This is again like the solution to the null space. So this solution is like xy equals to -5 minus 3 plus t times 5, 5. So this means what? This is a line that intersect the point -5 minus 3 with the direction 5, 5. Is this direction 5, 5 or not? What's this vector here? Yes, right. Yeah, so this direction is 5, 5. Okay. Yeah. Okay, how to find this direction? Okay, let's make it precise a bit. So here is P, right? Here is Q, let's say. Okay, we want to find PQ. Maybe to be precise, we should say this is all P, this is all Q. Right? Right? Okay. So how to find PQ? PQ is actually PO plus all Q. Correct? But OP is minus PO is equal to minus OP plus OQ. So if you want to find the point from Q to P, then you need to swap this formula. Okay, to make life easier, let's just swap these two. So let's call this OP. Hey, wait, I want to go from P to Q, right? Then I'm correct already. So here to here, correct. Okay, correct or not? Yeah, I think I'm correct. Yeah, so what is this? Minus OP is what? In our case, is 5.3, right? Plus OQ 0.2. So I get 5.5. Okay, so this is the direction from P to Q. Maybe I change this to differentiate between points and vector. Okay, yeah. So this is the direction PQ here. 5.5. Any question? Any question? No? Okay. So you see, I have a different parameterization here. Then you can do the line integral again. You should get the same answer. Okay. You can see that this x prime and y prime have different derivative now. Okay, they have 5 instead of 1 here. Okay. But at the same time, the time interval change from 0 to 1 instead. Okay, you can see that. You see, the time interval here get transported into the derivative. Okay, and see or not? See the one here. The one before appears in the derivative, but the one after appears in the length of the time interval. Can see or not? But previously, the time interval is length 5. And then your derivative become 5. Okay, so they are compensating the changes. Does it make sense? Make sense or not? Okay. Okay. Yeah. Okay. So the compensation here will give you the same line integral. Okay, any question about this? Okay, if no question, we continue our computation. I will finish it. We need to compute for C2 as well. Okay, we have to compute for C2. Or do you want to try yourself? What is C2 first? Go and try. Compute what is C2. I give you 5 minutes. Because the parameterization already give you already. So you just fix your T. Okay, fix your T. Try and find the line integral. And then shout out your line integral once you get it. Okay, let's try and do C2. And then tell me what's the final answer you get. So you need to start with parameterizing your curve first. So you need to start with parameterizing your curve. So you need to tell what is your ST, what is your YT. Okay? How your position depend on your time. Okay? How your position depend on the time. calculating. Huh? What do you get? 1169 over 3. No? I think so. Oh, who's that? Yeah, 245 over 6. Yeah, she get 245 over 6. I got 245 over 6. Okay, let's tell us what parameterization you use. So your time is going from where to where? Okay, so this is the easiest one. Anyone use different parameterization other than this? Jack, you use different one or? So you use the same parameterization. Anyone use different one or not? You also can set st equals to t if you want. But then you need to pick now. Okay, if you set x equals to t, you need to pick y to be square root, positive square root, or negative square root. Okay, so you need to decide this curve here is on the positive square root side or on the negative square root side. Yeah. So actually, you should, this parabola is something like this, right? Okay, so you need to pick whether it's on the positive side or the negative side. Which one? Negative. Again, then you need to pick the negative one. Okay or not? Right. So if you happen that you pick another C2, xt equals to t, then yt you need to pick in whether it's correct or not. So it's 4 minus x minus. Is that right? Yes. Mm. 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 Like, all right. Actually, there are two parts of it. Is it? Like there are two parts. Because minus is just the bottom part. Yeah, bottom part only. So you need to take you need to take two parts actually. Split into two parts. Yeah. Yeah, split into two parts. Yeah. So the left right part is divided by your time. By your time. So my time is going from -5 to where? To 0, then it's this part. And then the other part is a different time. Okay, so actually there's two parts here. So it is negative when time is going from -5 to 4. Okay, and then you take, this is for y1t, and then you should take another one. So you should take another one, y2t, which is square root 4 minus x. The time is going from 4 to 0. So your time run backward. Okay, so this is a time traveling. Right. So if you pick this parameterization, you go forward in time and then you go backward in time. Cannot. Okay, but if you pick the Larry ones, you don't go backward in time. You just because you go from negative y all the way up to t equals to 2, y equals to 2. Okay, you just go upward. But if you go the direction in x, you have to go forward in x and then you come back. Yeah, yeah. Okay, so you will split into two parts if you want to use the other parameterization. All right, so you just use this and then you integrate. So let's use the C2 instead of C2 prime. You can try this again. Try this line integral. You should get the same answer. Let's try this line integral here. So if we try the Larry one, we should start with integrate c y squared dx plus x dy to be equals to c of integration over c2 y squared dx plus integration of c2 x dy. And then you just substitute your integration domain, okay? And then y squared and c2 become e squared, okay? And then what is the y prime, x prime here in the x direction? You get minus 2t. Okay, so time minus 2t dt. Okay, plus c2 again, so minus 3 to 2. X become 4 minus t squared. And then what's the derivative in the y direction? You get 1. 4 times 1 dt. Okay, and then you do this computation here. You should get 245 over 6. Okay, so first you integrate over c2, you get 245 over 6. And then you integrate over c1, you get this which one? Minus 5 over 6. Okay, so what it says here is even though these two curves have the same endpoint, but they might not integrate to the same number. Okay, no? Okay. So endpoint doesn't affect endpoint will affect same and different curve with the same endpoint might give you different line integral. Okay. Different parameterization of the same curve will give you the same line integral, but different curve with the same endpoint might give you different integral. Okay, no? So although both curves starting from minus 5, minus 3, and end at 0, 2, they give you different line integral. Okay, make sense? Okay. Okay. Next is about this orientation. So what's the difference if I go forward in time and go backward in time? Okay, over the same curve. That should give you the negative of the other line integral. Okay, that should give you the negative of the other line integral. So this is like what you have learned in calculus 1, right? If you integrate from AB of fx dx is equal to minus of swapping the endpoint. So meaning you swap the direction. Okay, you swap the direction. So integrate of minus c is equal to integrate of c. So minus c means what? I go to the different direction of c. Okay, if I say minus c. Okay, no? Does it make sense? Okay, so this is a generalization of generalization. So if you change the orientation of the curve, it's just a negative of the integral of the original curve. Okay. So orientation of the line, there's only two ways. Okay, either you go to the left, either you go to the right. Okay, go forward or go backward. So when I change the orientation, meaning I change from forward to backward or backward to forward. Okay. Next. Okay. Question? Any question or no? No? Okay, so this is a generalization of what you learned in calculus 1, right? You can change your starting and ending point by introduce a minus sign to your integral. Okay, so in our higher dimensional case, we say that it changed the orientation of the curve. Okay, make sense? So in this way, I can write that integration of a line integral is equal to the minus of the line integral over the different orientation. Okay, make sense? Can you see the similarity between these two equations here? Okay, I put a minus and then I swap the order. Okay, I swap the orientation of my curve. Okay, so this tells you how you go forward and backward between line integral that have different orientation. Okay, so similarly, we can do line integral in three-dimensional space. Okay, three-dimensional space by introduce an extra derivative here. Okay, to your formula. That's it. And then we can write this square root, this long square root term as a norm, right? As a length function of your curve. Okay, so this notation is very useful. Later we'll use this notation here instead of writing all the x, y, z out. Okay, this RT here is kind of useful. Okay, because what is RT here? So RT here is really the curve, or the space curve, right? RT is equal to this vector here. Okay. Okay, so we will skip the example. Okay, you can try it because it's just one dimensional more than what we calculated before. Okay. Yeah. Okay, any question up to so far? We will keep work done to the next lecture. Yes. See the answer from the last page. This page. Which page? This page. Yeah. 5/6. This one is for C1. C2 is 245/6. Okay. Any questions before we take a break? A longer break. Lunch break.